Okay, so moving on from drawing into shape, we're still going to be talking about um, the molecules and their positioning, but now talking about the three-dimensional shape in molecular geometry. So most of you should have gone through valence shell electron pair repulsion theory, which is also called Vesper sometimes. The Vesper theory shows that in covalent compounds, valence electron pairs strive to be as far away from each other, and they want to do this to minimize electron-electron repulsion. And this effect is one basis of the geometries of molecules. So because of this electron-electron repulsion, we know the geometries, the shapes of molecules that can exist. Now, if you need a refresher on how we've gone from electron-electron repulsion pairs and made shapes, I suggest that you watch the video that is linked. It's actually a nice video showing using balloons, and naturally balloons will form the exact shapes that we predict for molecules when you put them together, depending on how many balloons, or in this case, we're thinking of them as electron pairs, are tied together, will always form the same shapes. So based on the Vesper theory, we know, for example, that methane, which has 4 groups on it, 4 bonding pairs, will always form a tetrahedron. And tetrahedrons, when you have 4 things connected at a central atom, always is separated by an angle of 109.5. That's for any tetrahedron, but of course in this example we're using methane. This is a number I suggest to remember. This number is going to keep getting brought up over and over again. So let's think about how we actually go from electron pairs and electron groups to shapes. So one of the key things that you need to understand for Vesper theory is that we're counting the number of electron groups attached to a central atom. And electron groups, we're going to define this as 2 different things. They can be lone pairs. Now remember, lone pairs on the central atom. So lone pair, unshared, or non-bonding electrons, all of those words are the same. Or they can be electrons that are making a bond to another atom or onto the rest of a molecule. And a multiple bond, so anytime you have a double bond or a triple bond, we still just treat this as one single group. So here's an example. In this first example, carbon is our central atom. We have you can see there are no lone pairs, no unbonded pairs on the carbon. So there's no electron groups from that. We have a group here where it's connected to a hydrogen. We have a group here. It's forming another bond to a hydrogen. And remember, we count double bonds as 1. So 1 other group here. So this carbon has 3 electron groups that it is attached to. In our next example, our nitrogen is the central atom. When we look at the lone pairs, electron pairs, connected to the central atom, you can see that there is 1. And we are going to count that as one of the electron groups. So I like to draw a circle around it to remind me that is a group. And then any other bonding electrons where we have a bond forming is also a group. So here, here, and here. So this has 4 electron groups. Okay, so in our next example, I want to remind you that we're always looking at the central atom. Now, these oxygens have lone pairs on them, but our central carbon does not have any lone pairs on it. There are no lone unshared electrons on the carbon. There are, however, bonds. They're bonding electrons. So this carbon forms a bond to an oxygen on its right. Remember, double bonds counts as one. And it forms a bond to the oxygen on its left. So it is only making connections. It has 2 electron groups. That's first how you count the electron groups. Electron groups are going to give you the shape of the molecule. So based on the number of electron groups, you can figure out the shape. Here is another point to remember, which is that when we're looking at the electron groups of an atom, unshared electron pairs are considered larger and more repulsive than bonded pairs. So bonded pairs create a little bit less repulsion than unshared pairs, unshared electrons. So in our example here, these electron groups in the first one all have the same type of electron group. They're all bonding electrons. These all are the same. In number 4, we see that the lone pair, there's one lone pair and 3 other bonded electrons. So just as a reminder, you can kind of like color this in or make it bigger. Just be reminded that lone pairs are going to repulse a little bit more. And again, in our last example, there are no lone pairs. We just have bonded electrons. So these are going to repulse in the same amount. So we can use this information with our table here. The first thing you want to know is the number of electron groups that you have. So again, here you can see this, our first one was 3, 4, 2. We'll tell you firstly the arrangement of electron pairs. So if you go to this part in our table, simply if you have 4 groups, electron groups attached, any type of electron group, lone pair or bonded pair, doesn't matter, you will make an arrangement of a tetrahedral. So in our example, this is for 4. An example up here, methane has CH4, that is 4 groups. So its arrangement is a tetrahedron. Water has 2 actual elements attached to it and 2 lone pairs, so 4 total, tetrahedron. Ammonia, we did ammonia as an example. Ammonia has 3 bonding groups and 1 lone pair, so that's also 4 total. And you can see you go through, if you have 3, you get a trigonal planar. 3 is trigonal planar. And if you have 2, then you're linear. That's pretty straightforward. You either have tetrahedral, trigonal planar, or linear. Now, the next piece of information to go from arrangement to the actual shape, you're going to have to think about how many of those electron groups were lone pairs because they repulse a little bit more. So in our top one, we can see methane, water, and ammonia are good examples. Methane has no lone pairs, and so it's still just a tetrahedral for its shape. If you have 2 lone pairs like water, we're only going to look at the shape left over from the actual bonded elements, and so you get a bent shape. And similarly for ammonia, if you only have 1 lone pair, but you have 4 groups in total, you get a trigonal pyramidal shape. So different variations you can have when you have 3 things attached. Here in both of these cases, boron trifluoride and formaldehyde don't have any lone pairs, so they still just make a trigonal planar. Similarly, carbon dioxide, which is one of the examples we did as well, has no lone pairs on the central atom, and so ultimately it is still linear. So make sure that you look at this table, understand how you go from the number of electron groups. So here's the actual electron groups. And then how you get the shape, this is going to be based on the number of lone pairs. The reason you want to understand shape, and again, go back and review Vesper theory and shape, is because shape is important for reactivity, in particular for polarity and dipole moment. So we know that geometry of a molecule and polarization of bonds are connected. And from this, we can deduce the molecular dipole moment. So instead of just the dipole moment between a bond, we can actually figure out the dipole moment of an entire molecule based on the individual dipole moments and its shape. So here we have carbon dioxide. Carbon dioxide, we know, has a dipole moment between each carbon and oxygen, in which the electron density is being pulled towards the oxygens. They are more electronegative. Okay. But we also know that carbon dioxide is linear based on its shape, based on its molecular shape. It is linear, and so it will actually be three-dimensionally represented just like we have drawn it here, which is as a linear line. And because of that, each of the dipoles going to the oxygens cancel each other out, making it ultimately not polar. It has a zero dipole moment as a molecule. Here's another example. This is boron trifluoride. We saw this in the molecular shapes as well. It is a trigonal planar, so it's flat. It's flat like a triangle. If you were to lay this out, you would see that it's flat where each fluorine is on each point here and the boron is in the center. Okay, so if imagine that being flat, and we know that each of these bonds is very polar. So the fluorines are very electronegative. They pull electron density to them. They pull electron density into each of these corners. But overall, because of its structure, these dipole moments individually will cancel each other out, forming a net zero dipole. So each of the bonds are very polar, but ultimately the molecule is not polar. So again, structure and understanding the three-dimensional structure of molecules is very important for polarity and understanding how things can be polar. The key is that shape and symmetry are going to tell you the polarity. So another example here, we have carbon tetrachloride, carbon with 4 chlorines on it. Each of the chlorine atoms are very electronegative and compared to the carbon atom. However, because these are arranged symmetrically in a tetrahedron, the result of the 4 electronegative bonds being pulled actually ends up in a dipole of 0. This is a symmetric molecule. That's the key thing I'm going to say. It's a symmetric molecule in which the dipoles ultimately cancel each other out. However, if you have this molecule, methylene chloride, in this case, 2 of our connections are hydrogens instead of chlorines. You can see that this molecule is not symmetric anymore in its shape. We have an area that is negative and an area now that is positive, because the polar bonds are not equal all around the molecule. They're different. So in this case, the resulting molecular dipole occurs. We do not have a zero dipole. We actually have polarity on this shape, in which this side is slightly positive and this side is slightly negative. And that's only because of the symmetry of the molecule and understanding its shape. So again, remember, symmetric molecules that are completely symmetric, or if they have weak dipole bonds in between, are nonpolar. Symmetric things are nonpolar. Even if they have very, very polar bonds and they're symmetric, those bonds are going to cancel each other out. However, all other molecules, ones that are not symmetric, are going to be polar. And polarization of a molecule, where it is polar, is going to determine its chemical behavior and its reactivity. So it's very important to understand how shape and polarity are connected. Remember that structure, this actual structure and shape, is what determines the properties in molecules. Okay, and that is the end for this section of chapter 1.